Hey everyone, today we're going to be talking about estimating areas using geometry. And even though this sounds like what we did a couple days ago by using our geometric formula to calculate those areas, it's actually going to work a little differently today. So before we jump into that, I just want to review really quick the notation for integrals. Right? We have this integral from a to b of f of x dx, and that just means to find the area trapped between the function and the x-axis from x equals a to x equals b. Okay, so that's what we've been doing the last several days, using a variety of methods. And so we've learned that sometimes we can calculate these areas using geometry formulas. However, that's obviously going to work only for really specific graphs, right? When they form triangles or rectangles or trapezoids. And obviously that's not going to always happen. So the question for today is, what do we do when we can't get exact areas using geometry formulas? And so we're going to learn a method for that today. Now the difference today is before we were using geometry to get exact areas. Today we're going to use geometry to get estimates of those areas. And so what we're going to do is estimate the areas using rectangles and trapezoids. And so I'm going to show you how that works here. Okay, so now we're going to have 4 new ways to estimate areas. You'll see here the names. We've got LRAM, RRAM, MRAM, and the trapezoidal method. Okay, so if we start here, this stands for left rectangular approximation method. And a lot of times you'll see, especially when it comes to the test, instead of LRAM, you'll see this called a left Riemann sum. Okay, so let's say, just for this example, I'm going to call this function f of x. And let's say you were asked to find the integral from 0 to 3 of f of x dx. So the area between that curve and the x-axis between x equals 0 and x equals 3. Now obviously we don't have a nice geometry formula to fit here, but what we're going to do is use rectangles to approximate that. So for this example, I'm going to approximate it using 3 rectangles. So you can see I've got 3 subintervals here. I've got from 0 to 1, 1 to 2, and 2 to 3. Now, since I'm using a left rectangular approximation, that means for each interval, I'm going to use the left endpoint to find the height of that rectangle. So for example, from this interval from 0 to 1, I'm going to use this left endpoint at 0. I'm going to draw up to the curve, and I'm going to make a rectangle with that height. And I'm going to do the same thing for my other 2 subintervals here. From 1 to 2, obviously the left-hand point is at 1. I'm going to draw up to that curve and then over. So I draw a rectangle with that height. And then the same thing from 2 to 3. Do it up to the curve, draw a rectangle over with that height. Now you can really easily see here why this is just an approximation, right? Obviously I've left all of this area out, but this is a way that we're going to approximate these areas. So RRAM is going to work a lot the same way, right? In this case though, we have a right rectangular approximation. Or what we call a right Riemann sum. Okay, so again, let's assume we're evaluating the same integral. I'm still going to use 3 rectangles, but in this case, instead of the left endpoint, I'm going to use the right endpoint to approximate it. So on the interval from 0 to 1, 1 is my right endpoint, so I'm going to draw a rectangle that has that height. On the interval from 1 to 2, I'm going to use my right endpoint, Draw a rectangle with that height, and same thing from 2 to 3. And so obviously we could easily find the areas of those rectangles if we had a function, and we would add them up to approximate the area under that curve. Okay, MRAM now is our midpoint approximation. Get my hand out of the way here. Or midpoint Riemann sum. Now, this is exactly what it sounds like. We're still considering those same 3 intervals, but now the height of that rectangle is going to be determined by the midpoint of that interval. So from 0 to 1, I would go find the endpoint, or the midpoint, excuse me, and that would determine the height of the rectangle over that interval. So between 1 and 2, I would find the height at 1.5. That would determine the height of my rectangle. And again, if we had values here, we could find the areas of these rectangles, add them up, and that would be our approximation for the area under the curve. Now, the next one is what we call trapezoidal estimate, right? And here you can obviously get from the name, we're going to be using trapezoids to estimate those. Now, again, important thing to remember here, when we get into problems, the area for the trapezoid is going to be h over 2 times b1 plus b2. So that's a formula you'll have to have memorized. And here's how this works. When we're looking at a trapezoid, we're using both endpoints of the interval and then connecting those to make a trapezoid. It's obviously hard to see here. You'll get a little better picture. From 1 to 2, I'm going to draw both of those heights, and again, I'm going to connect. And then from 2 to 3 here, connect here, and I would find the area of these 3 trapezoids to estimate those areas. Okay, so let's look at some examples of how we would use these formulas to actually estimate the areas. Again, I want to be really clear that while before we were finding exact areas, these methods are going to give us estimates of the areas. All right, so I got a little ahead of myself here, right? So important to know, again, is that we're estimating. So when we use these approximation methods, we do not get the exact answer. Okay, and then obviously the size of our subinterval is going to matter. So the subinterval is how wide you make your shapes. So you can see here, right, this is like what we did on the first page. Each subinterval had a length of 1. Here it looks like we've subdivided that and made each subinterval have a length of a half. Now, if we have smaller subintervals, we get a more precise area. So the more subintervals we have, and you can see it here, right? It looks like I have less of an overestimate in this example. So the smaller my subintervals are, the closer my area is going to get to the exact area. All right, now we're going to look at some problems here. Okay, so they've given us the graph of x squared plus 3, so I've got my parabola shifted up 3. And we need to estimate the value of the integral from 0 to 4 of f of x dx. So we're going to estimate the area under the curve between x equals 0 and x equals 4. Okay, then it's going to tell us here, these problems are always going to tell us the type of approximation method, and they're also going to tell us the number of subintervals, which is going to be really important to pay attention to. So here they're telling me I'm using RRAM with 4 subintervals. So if I look, I was finding the area from 0 to 4. If I'm going to use 4 subintervals, that means each subinterval is going to have a length of 1. So really what I'm looking at, and I'm going to illustrate it here because this will help me calculate. I'm going to have the interval from 0 to 1, from 1 to 2, from 2 to 3, and from 3 to 4. So on the graph here, My interval from 0 to 1, it says I'm using a right approximation method. From 0 to 1, I'm going to use the endpoint at 1 and draw my rectangle. There's my first rectangle that I'd be finding the area of. Then I go from 1 to 2. I'm using the right endpoint, so the endpoint at 2. There's my second rectangle. Got from 2 to 3, here's my third rectangle. And then from 3 to 4. So when I do my calculations, what I'm really doing is finding the area of those 4 rectangles and adding them up to approximate the area that's under the curve. Obviously here we can see again, we're going to have an overestimate because each of these rectangles go above the curve. But again, we're just after an estimate here. So that's how it would look if we asked you to kind of graph or show the rectangles on your diagram. Now, when I calculate it, here's what I do. I've drawn out my 4 subintervals. Since I have a right approximation method, I'm going to find those y values at the right endpoint of each interval. And then I would just calculate f of 1. I'm going to use my function, or I could use my graph in this case. F of 1 is 1 squared plus 3, which is going to give me 4. F of 2 is 2 squared plus 3, or 7. F of 3 is 3 squared plus 3, which is going to give us 12. And then f of 4 is 4 squared plus 3, which is 19. So now, I'm doing areas of rectangles, which I know, obviously, the area of my rectangle is base times height. Now, the nice thing here is since we split up these subintervals evenly, my base is always going to be 1. So I'm just going to kind of factor that out. My common base is 1, and then I can add up all the heights. Right? So instead of doing 1 times 4 plus 1 times 7 plus 1 times 12 plus 1 times 19, right? That's each time is my base of 1 times the height of the rectangle. Instead of doing that, when I have just a common or an even base, I'm just going to pull that out front and do my heights. So now if we add those up, get my calculator here. Let's see. So I get 42. So what we're saying here is that the integral from 0 to 4 of f of x dx is approximately 42. I don't want to say it's equal because we know that's not an exact answer, but it's approximately 42. Okay, so now we're going to go through the other 3 methods, but a lot of the work is going to look the same. So again, now I'm using LRAM. I have 4 subintervals again, so I know that's going to be 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Now if I were asked to graph it, I start at 0. Now since I'm using left interval from 0 to 1, I'm going to pick that left endpoint and use that as my height. From 1 to 2, again I use the left endpoint as the height of the rectangle. 2 to 3, I'm going to use this endpoint. And then 3 to 4 is here. So now if I'm looking and comparing these, right, my right approximation gave me an overestimate, and it's pretty clear that I'm going to get an underestimate here because I'm not accounting for all these areas. So I would expect that this is going to be a smaller number. So let's do the calculations now. I'm using the left endpoint this time, so I'm going to draw on those left-hand y values. F of 0 is going to give me 3. F of 1 is 4. Let's see, F of 2 is my next one with 7. And then F of 3 is 12. So again, I have a common base length of 1. That's always 1, so I can factor that out. And then I have 3 plus 4 plus 7 plus 12, which gives me, let's see, 7, 7 is 14, 26 here, if I did that right. So now the integral from 0 to 4 f of x dx using a left approximation is approximately 26. So you can see here these numbers are pretty different by using those different methods, especially because the number of subintervals is fairly low, so we're not getting very precise areas here. Okay, let's check out midpoint next. Again, well, actually we changed here. Now we only have 2 subintervals. So if I'm finding the integral from 0 to 4, I'm pointing but you can't see that. The integral from 0 to 4, and I only have 2 subintervals. Now that means my subintervals are from 0 to 2 and 2 to 4. So on our graph here, if my first interval is 0 to 2, obviously the midpoint is at 1. So I'm going to draw a dotted line here, and I'm going to use 1 to find the height of that rectangle over the interval from 0 to 2. So there's my first rectangle. 2 to 4, that midpoint is going to be 3, so that 3 is the height of that whole rectangle. So I only have 2 rectangles in this case. Now, when I show my work here, I'm going to draw my line in the middle to represent that midpoint value. So now my midpoint is 1. F of 1 I know is 4. In this case, my midpoint is 3, and I know f of 3 is 12. So now the only thing I have to be careful of is when I do my base times height, my common base length here is 2, and then I have 2 times 4 plus 12. Which is going to give me 16 times 2 is 32. So now in this case, our area using this approximation method is approximately 32. All right, so then the last one we have here is our trapezoidal. And again, we're using 4. So 0 to 1, 1 to 2, 2 to 3, and 3 to 4. Now, first we'll draw in the picture, and again, this might be hard to see because the picture is pretty small. But the idea here is I'm finding the heights at both endpoints and then connecting those endpoints. And I kind of exaggerated so we could kind of see that trapezoid. Again, remember in this case, the trapezoid is on its side. So this, what we are calling the base of our what we are calling the base of our rectangles is the height of the trapezoid because that's on its side. Then we're going to talk about we'll have a base 1 of our trapezoid and a base 2. I know that's really hard to see there, but the idea is the trapezoid is on its side. So since I kind of filled that in, I won't worry about drawing in the other 4 trapezoids. But what we need to know now, again, this subinterval is going to be the height, the height of our trapezoid. Now we have to figure out the bases, so we're looking for the values at both endpoints this time. So again, we're finding function values here. F of 0 is 3, f of 1 is 4, and I have that twice. F of 2 gave us 7. F of 3 was 12. And f of 4 was 19, excuse me. Now remember, we said again our area formula is h over 2 times b1 plus b2. So we have a constant height of 1. So I'm going to go ahead and pull that out. So my height is 1/2 for all, or my h over 2 is 1/2. And now I'm just going to add up all the bases I have here. So I have 3 plus, I've actually got 2 times 4, because 4 and 4, plus 2 times 7, plus 2 times 12, plus 19. And so now I'm going to plug this in so I don't make any mistakes here. And I get 34. So my approximation in this case is 34. So that's the basics of how this is going to work. We're going to look at a few more examples. This is a little different because we had a function. We'll also be doing problems where we're just given a table and asked to find these same approximations. So we're going to go through 4, and these actually turn out to be a little quicker because you're not having to compute y values. So it's giving us the table for a function f of x. And it's asking us to estimate the value of the integral from 0 to 9 of f of x dx using the approximation that's given. All right, so in my first one, I have a right rectangular approximation with 4 subintervals. So we're going to use the 4 subintervals given to us by the table. So I have 0 to 3, 3 to 6, 6 to 8, and 8 to 9. And the first thing I need to notice is my bases of these rectangles are not all the same. Here I have a base of 3, 3, then 2, and then 1. So since my bases aren't the same, I can't kind of factor out that common base. So we have to keep that in mind when we do our calculations. Now it says I'm doing a right rectangular approximation. So I'm going to take all my right endpoints, and I'm just going to grab the values from the tables. So f of 3 gives me 5. F of 6 is 4, f of 8 is 6, and f of 9 is 8. So now again, I can't pull out a common base, so I have to do the base times height for each rectangle. So I have 3 times 5, so the base length was 3, the height is 5, plus this base length is also 3 times a height of 4. Now I have a base length of 2 times a height of 6, and then last, a base of 1 times a height of 8. So let's see if I add 15 plus 12 plus 12 plus 8, I get 47. So in this case, the integral is approximately 47. Okay, at this point, since the video has gone long, let's use these next 3 questions to kind of review quickly before you get started on your practice in class. So we'll wrap up here and talk about these when we're all together in class. All right, thanks for hanging in. See you tomorrow.